Miguel, empieza la transmisión.
Listo, profe, ya.
Listo.
¿Listo? ¿Estamos? ¿Largamos entonces?
Sí, cuando quieran.
Okay. So, thank you for joining us and welcome to a new edition of the series of webinars organized by Alma and Latin American Magnetism Association. In case you're interested in our activities, you can find us in the web or in our Facebook page. And in case you want to reach us, you can also email us to this account, almamagnetism@gmail.com. We strongly encourage young researchers in the area of magnetism and magnetic materials to join us and participate in different activities of interest to our community, which can also be found in our newsletter. You can email us to be added to our distribution list in case you are not already listed. Our association is composed of different nodes, and we hope we can soon include representatives from other Latin American countries. So far, we have members from Mexico, Colombia, Peru, Chile, Brazil, and Argentina. This year's webinar committee is formed by a very nice group of efficient and hardworking people who invite the speakers and organize the webinars. As you can see, all the nodes are represented by at least one member. If you couldn't attend or missed our previous webinars, you can find them in our YouTube channel, to which you can also subscribe. Today's talk will also be available in this site. Our speaker for today is Santiago A Grigera from La Plata, Argentina, and his talk will be about investigating the nature of a geometrically frustrated magnetic material, which is a spin ice. As usual for our webinars, this talk is being streamed via Zoom and our YouTube channel. We also have confirmed speakers for the upcoming webinar, so you can pin up the dates in case you are interested. Without further ado, please let me introduce to our chairman for today, who is Rodolfo Borsi, an Argentinian scientist whose current research interests are new forms of order in condensed matter physics, experimental and computational studies, strongly correlated as well as frustrated systems and magnetism. Rodolfo is the right person to tell us more about our speaker of today. So, Rodolfo, the floor is yours.
Okay, thank you very much, Paula. Let me then introduce Santiago. I'll try not to annoy Santiago by being a bit brief. So Santiago studied physics at La Plata and did his PhD with Paco de la Cruz at BT, as we call it, the low temperature physics group at Bariloche. He then moved to the UK around the year 2000 and then started a PhD working within Andy Mackenzie's group. This was first in Birmingham, and then he moved with all the group to the University of St. Andrews in Scotland, where he reached the position of reader. Around 2007, he started working on frustrated magnetism, the topic of today's talk. His paper on the measurement of magnetic monopoles in spin ice, published in Science in 2009, has today around 640 citations, according to Google Scholar. His work on this topic, together with that of other researchers, Alan Tennant, Frederick Messner, Stephen Bramwell, among others, deserves the Condensed Matter Division Europhysics Prize in 2012, which is one of the most prestigious prizes in the field of condensed matter physics. Since 2010, we've been lucky, and he's established now in Argentina. He's now the acting director of the Institute d'Iflicip, which is the institute where I work, in the city of La Plata, where he runs the low temperature physics lab of La Plata. So I'll end the presentation saying something which is not currently in any CV, which is that physics is nice. Physics is nice. Not only doing physics is nice, not only because physics is nice, but also because sometimes you can choose to work with the people you want to work. And luckily, this has been my case. So doing physics with Santiago during these many years has been really my pleasure and sometimes my comfort as well. Together we have worked like mad at very absurd hours at night. We have sometimes laughed our heads out in the lab or talked in the lab about films or books. And other times we have secretly had to talk in whispers during asados or meetings about physics, about papers, or about naughty instruments that were refusing to do the work they were supposed to do. What I mean is physics with life altogether, which is really the way probably it should be doing it, at least a way in which you can do it. So this was the first time I had to introduce Santiago, and I hope I have done it more or less well. It is again my pleasure now to leave you with him, who will tell you about some of the spin-ice physics, which is a nice topic to talk about.
Okay, thank you very much, Chufo, for your warm introduction. Although you said you won't embarrass me, you did. But anyway, thank you very much for the introduction. And I should start, of course, by thanking the organizer for the invitation to give this talk. I'm very happy to be here giving this talk. And I should say that indeed, I'm one of those persons who watches this talk on the YouTube channel afterwards, rather than all the time when they're taking place. Okay, so as I said, the idea today is to tell you some work we've been doing on spin-ice materials. Let me see if this works. Okay, so let me start by acknowledging the people I have worked with. As Chufo says, one of the nice things about this work is that you can work with the people you like to work with, rather than the case in other works. And so of the things I'm going to be talking you today, I want to highlight the participation of Chufo, Rodolfo Borsi, Lucas Pili at La Plata. And for the second part of the talk, I want to highlight the work of Alan Tennant and Anjana Samarakun, both at Oak Ridge National Lab in the US. And in all cases, I'd like to highlight the participation of Andy Mackenzie and Roderick Messner. Roderick, of course, on the theory side of this work. So let me start by explaining the title, if you want. So some few words about frustration. So of course, frustration is nothing alien to us. I mean, we are physicists, scientists working in Latin America. Most of us work in Latin America. So frustration, definitely something we experience on a daily basis, I would say. But the point here is not frustration. The point here is to discuss frustration in magnetic materials. And the idea here is that, or one of the definitions, general definition of frustration is to say that you have a system where you have a Hamiltonian that has competing interactions, and it's impossible to minimize the energy for all those interactions simultaneously. Okay, so maybe let me do a bit of history here. Maybe the first one to recognize the importance of or the interest of frustration was Anderson, like with many other things. It is said that he wrote during one lecture he gave at Aspen in 1976, frustration is the name of the game. And so the first paper, so the first time this has been put in black and white, is this paper by Toulouse in a journal, but by the way, it doesn't exist anymore. This is Communications on Physics from 1977. I tried to find it, but apparently it only lasted a couple of years. This is a very nice paper. So one of the first things he says is that he's borrowing this word frustration from a lecture that Anderson gave at Aspen. So that sort of matches this history going around that Anderson was the first one to say it. So Toulouse is working, he's thinking about problems in spin glasses. So he's interested or worried about disorder, and he poses this question. This I've taken from the paper itself. It says, how does one distinguish serious disorder from non-serious disorder, and how can one measure that? And he goes the way to find the answer to that. And of course, the answer to that is frustration. So the way in which he starts is he said, okay, let's consider a very simple system. This is just a square lattice, and we have Ising type spins, and we have pairwise interaction J-A-J, so minus J-I-J, S-I, S-J. And then he says, okay, let's start with some ferromagnetic configuration. That will be here. This is all side, so all interactions are positive, that means negative. So this is a ferromagnet. And then he says, I flip 4 bonds, just at random. I choose this configuration. And this is a disorder configuration. But as he said, this is not serious disorder, because, of course, in the ferromagnetic case, I can put all spins pointing up, and I'm putting blue for it pointing up. And then if what I take for the second case is I just flip 1 spin and make it point down, then this disorder is no longer important because all bonds are satisfied without any problem. So he says, what I'm going to call serious disorder is what comes from what I would call the frustration effect. When I say I mean Toulouse, of course. So he proposes this case in which you have 3 positive bonds and 1 negative bond. So 3 ferromagnetic, if you want, and 1 anti-ferromagnetic. So then he says, look, there's no way in which I can fully satisfy this bond, no matter which configuration I take. If I take a completely ferromagnetic one, there's this bond that doesn't work. If I take an anti-ferromagnetic bond, this bond works, but this bond works, but this other bond doesn't work. So then he says, okay, there are other ways in which I can also get frustration, and let me review some of these ways and now give also an experimental vision on those. So first is the one I just mentioned, the one he gives the long example on, which is disorder. Then another way in which you can frustrate the system, this same system, is by adding further neighbor interactions. So you have an anti-ferromagnetic square Ising lattice, and now you add 2 more next nearest neighbor interactions, then you see that there's no way in which you can satisfy. If you put an anti-ferromagnetic configuration, the next nearest neighbors are frustrated. If you put some kind of way to satisfy these bonds, you mess the others. And the third way, or a third way, is to have geometry being the one that makes the frustration. Although you cannot say that this is geometry too, but what I mean here is just pure geometry with just nearest neighbor interactions, right? So if I have a triangle, I have anti-ferromagnetic interactions between the bonds in the triangle. There's no way I can satisfy one of the bonds. Is always going to be complaining about what's going on. So from an experimental point of view, maybe also from theory, disorder is not something which is particularly nice. It's not very easy to do calculations with disorder. It's not very easy to control experimentally. And then the second case poses no problem from a theoretical point of view. You can very easily say I have an interaction to next nearest neighbors, which is exactly the same that to nearest neighbors. But experimentally, this is a nightmare, and it really requires fine-tuning. So it's not easy to get a system where you will have where you will be able to tune different interactions in this way. So geometrical frustration seems to be the best way to start working on frustration. So there's already a lot of work on geometrical frustration. So here I put some examples and some of the advantages. As I said, these are clean systems. They have strong correlations. Because they are frustrated, they avoid the trivial solutions. And you can find things like solids, liquids, gases, ice, which is the topic of today. And then you find fractionalization of charge, fractionalization of excitations, quantum liquids, post-condensation, etc. Okay, so the case I want to tell you about today involves essentially tetrahedra. So let me start by looking at one Ising tetrahedron. So we have 4 spins at the corners of this Ising tetrahedron, and they can point, they're Ising in the sense that they can point either out or in. They cannot point in any other direction, right? And they are classical. So we're taking the simplest possible case, which is classical spins, and we take a nearest neighbor Hamiltonian. So the first question is, what's the ground state of this tetrahedron? Okay, so we explore the configurations. There are not those many, because it's pairwise interactions. We take a pair of spins, and you see that I can either put these pairs, this pair of spins, one pointing in, one pointing out, or both pointing in and both pointing out. So now, if I look at the components of this magnetic moment, you see that when I have a configuration which is either out-in or in-out, that tends to favor a ferromagnet. You see that here the long moments are the green ones, and they're oriented ferromagnetically. So if I add a ferromagnetic interaction, they would favor these configurations, while the both pointing in or both pointing out are predominantly antiferromagnetic. So an antiferromagnetic interaction would favor this as a ground state. Right, so for a single tetrahedron then, a ferromagnet doesn't decide what's exactly the ground state. I have 6 possibilities, because the only thing that it's telling me, and this is what we're going to call the ice rule, is that I need to have, of these 4 spins, two of them should be pointing in and 2 of them should be pointing out. Okay, so this is a single tetrahedron. Now, if I want to combine tetrahedra and create a lattice, the one I'm going to combine is, or the one we are interested in, is a pyrochlorlattice, which is essentially putting this tetrahedra together by the vertices. So if you do that, then now you need to think, okay, what are the different possibilities? What are different configurations I have for such a lattice obeying the ice rules? And what you find is that you get an exponential number of possibilities. So you get a residual entropy. So the way in which you can do this calculation is very easy. You have for each tetrahedron, because they are they're sharing, you have only 2 spins. So I have a factor of 1/2 here, and then of the 6 choices I had for one tetrahedron, there's a 1/4 chance of matching the spins with the neighboring tetrahedron, right? So that gives me the 6/4 becomes the 3/2, and this is the same number that you get for ice, and that's why for water ice, and that's why people call these materials spin ice. So there's another way of making this calculation. This is something that Onsager mentions in a paper from 1944, which is, I think it's a very nice idea. He says, okay, if I want to think about the configurations, of course you're thinking of water ice, but it's exactly the same thing here. Because the way in which I can think of this is, what if I try to thread a string going through all the vertices of this tetrahedra? If I think of the ways, you see here, essentially what we're doing is we're following spins and we're threading some sort of a string. If I think of what are the possible configurations of the string threading all these tetrahedra, then I'm going to get the entropy of water. And I will see that would be helpful for thinking about this ground state. Okay, as I said, this is an experimental talk. So we need to talk about materials. So essentially, we're going to be discussing 2 materials: the dysprosium titanate and holmium titanates. They have a nice pyrochlor lattice of the dysprosium or the holmium. which are the magnetic moments. Titanium is non-magnetic here. They're Ising type spins in the sense that because of the crystalline field, they're essentially, you need an energy, you need a temperature above 300 K to excite them away from the Ising states. And we're going to be working below a couple of Kelvin. So they're, for all extent and purposes of our work, they're nice, well-behaved Ising type spins. You have ferromagnetic interactions between 1 and 2K, and they have big magnetic moments of the order of 10 Bohr magnetons. So we grew some crystals using this floating zone. The dysprosium titanate is from our lab, and the holmium titanate comes from Prabhakaran in Oxford. And for the dysprosium titanate, we used not naturally abundant dysprosium, but we use an isotope of dysprosium, because for two reasons. One is that naturally abundant dysprosium absorbs neutrons a lot, so it's impossible to do neutron experiments with that. And the other is that this isotope we use has no nuclear moment. So what we're going to be, essentially, we wanted a system as pure as possible. Okay, so what people did for spin ice is the same thing that people did for water previously. So I think it's a paper from 1933, Choquet, who measured specific heat for ice, integrated it out, and saw that there was a missing part. So if you assume that you start from 0 entropy at 0 temperature, you see that you don't reach. So you don't reach the entropy expect, which is essentially R log 2, and the missing bit corresponds to the residual entropy. Right, so people did exactly the same thing for spin ice. This is a work by Ramirez in 1999, and you see that the residual entropy is very well described by Pauling's entropy. Okay. Oops. Yes. Okay, so going back to this idea of Onsager, this idea that you can think of the system as some sort of a yarn where you have all these threads or these strings going around the system. It's very good to realizing that this means that the system might have a very high entropy, but it's not completely disordered. So you expect to find correlations in the ground state. And when you do the calculation, what you find is that what you get are dipolar correlations. So one way of checking whether the ground state you're looking at is the one you expect is just to, okay, this is the calculation, what you will get from these correlations in reciprocal space. And if you do, you can do now a neutron experiment and check for these dipolar correlations. So this is again what theory predicts, and this is what you get when you do neutron diffraction from dysprosium titanate. I know the data is not pristine, but you see that the main features are essentially there. So you see that the parts where you expect to have maximum intensity is where you get maximum intensities, and these parts where you get these characteristic pinch points that are talking about these correlations are essentially parts where you get less counts. So it's going in that direction. So the one thing you can ask is, where are these dipolar correlations coming from? Is there any relationship between these rules I have for the ground state and some sort of electromagnetic rules, if you want? And the answer is that yes, there is. And you can see it in the sense that in Onsager's argument, this idea that you were threading a string through all these corners was already talking of some sort of conservation. And as you see, essentially the Irish rules are telling you that because you have 2 in and 2 out, essentially what you're saying is that the sum over those 4 on each tetrahedron should give you 0. So essentially that's telling you of some sort of a conservation law. And if you go from this discrete version to a continuum version, that conservation is expressed in terms of divergence-free fields, And of course, once you have that, you can think that you can write that as the curl of some vector potential. And now you can use a sort of a different language. You can think that your ground state comes from a system which has no charges corresponding to the field, and excitations would correspond to local creation of charges, right? So once I violate this divergence-free condition, I'm going to get charges. And what you see is that because of here you have Ising spins, you get these two flavors, only two flavors of charges. If you have some sort of a Heisenberg system, you get more flavors of charges. You can have charges which are either positive, let's say, or negative, and you can either have single valued, so +2 here, or double valued +4, or -2 and -4. And you see that you get 8 possibilities of a single charge and 2 possibilities of a double charge. And when you look at how these charges interact with each other, you see that they obey magnetic Coulomb law. So essentially what you got is a mapping, if you want, between the excitations here and particles that look like monopolar excitations. So one of the nice things about this is that now not only can you describe your ground state, but you can describe excitations. And because your system is formally identical to a system of charges, you can pinch results from other, for example, from electrolyte theory, and use it for spin ice. So here, for example, what we're saying is that you can take now the bi-Huckel theory and calculate the specific heat for spin ice, right? You just replace the electrical charges by these magnetic charges, and you use exactly the same formulation. So here, what I'm showing is the heat capacity as a factor of temperature. The squares are the measurements we did, and the two lines correspond to two calculations. The first one is a Bethe lattice or Husimi-tree calculation. Essentially, this is assuming that the correlations die away very easily, and as expected, they work very well at high temperatures, but they don't work well at low temperatures. And the blue line here, if you can see it, corresponds to the bi-Huckel theory. And you see that at low temperatures, when you expect this description to work, right? This description would only work if there's a number, not too big a number of excitation. The description works very well. Okay, so essentially that's the brief introduction I wanted to give you about spin ice, and now I want to tell you about two different problems in spin ice in which we've been working on. One of them, this one in particular, where it's still work in progress. So what I want to tell you is about a topological transition you can get in spin ice. The idea is this: now you take your spin ice material and you apply a field along one of the principal axes, let's say 100. If you do that, you polarize this ground state and you get a single state. So you lose this residual entropy, you get a single state with 0 entropy. And now we're going to consider what happens when you look at excitations in the case where the temperature is much smaller than your exchange constant. Okay, so this is your pyroclore lattice. This is 100 direction. Allow me to project this. So this wants to be some sort of an eye. I'm looking in that direction, and now I project this onto a plane, and I'm putting a field along this direction. And as you see, when I do that, I polarize spins all in that direction. But this direction is special in the sense that it's the spins, so the configuration I get belongs to a spin ice configuration. You see that in each tetrahedron, these yellow squares are the tetrahedra. In each tetrahedron, I get 2 spins pointing in and 2 spins pointing out. So essentially, the field not only is not going against, but it favors the ice rods. So what sort of excitations do I have of this system? Well, one way would be to flip a spin, but as I said, because flipping a spin means that you would pay something like 4 times J. So, and we're working in the limit where this is too expensive. So KT is much more than J. So these are not allowed. But even in this limit, you can get some other type of excitations, and these excitations are these strings. You see that here, what I've done is I flipped a whole line of spins. So you see that now these red spins point down, but when you go to each tetrahedron, still you have that 2 of these spins are pointing and 2 are pointing out. So for these excitations, you don't pay any energy in terms of J. So even if J is infinite, these excitations can still exist. And once you have them, of course, they're free to move. You see, I can move them, and I'm still obeying the Gauss rule on each tetrahedron. Okay, so let's do a bit of statistical mechanics. This is from a work by Chauvert and collaborators. So each time, because I have an applied field, each time I flip a spin, that cost me, and this is because of the geometry, 2 over square root of 3h. But also, each time I propagate one of these strings, I get an entropy, associated entropy per link, which is log 2, right? Because when I'm propagating this string against the field, I can either go in that direction or that direction, right? So when we construct the free energy, we essentially have this term coming from the Zeeman term and the entropic term. So essentially, I have a critical field when this free energy is equal to 0, and that separates 2 regions. One region at, if you want, high field or low temperatures, where the entropy is 0. There are no lines here, and then another region where I get these strings or lines that appear spontaneously and reduce, for example, the magnetization of a sample. So that brings me exactly to this. So what kind of observables do we have of this kind of transition? This would be the magnetization as a function of temperature of magnetic fields. This here is this Castelline line, so this line of transition. So above that line, there are no strings, so no lines, and the magnetization is equal to the saturation magnetization. But below this transition, I start adding these. So spontaneously, the system starts having these string excitations, right? So this is the 2-dimensional version I showed you before. It will be the 3-dimensional version in the pyrochlore lattice. And as you see, these are lines of negative magnetization. So each time I put one of these, the magnetization decreases. So if I look, let's say, at constant temperature, what I expect to see of the magnetization as a function of field is something like this. So above the transition, it's perfectly saturated. Below the transition, there are these lines or these strings that lower the magnetization. So if I now look at the susceptibility, this would be one of the most distinguishing features of this type of transition, in the sense that what I get is that I get something that looks like a divergence susceptibility in the low field side. This is where the strings exist. But because there are no excitations, absolutely no excitations on the high field side, there's nothing here. So this is why this transition was first discussed in the context of Dimers and Nagler, Steve Nagel suggested that one should call this type of transition 1.5 order transition. It says that from one side it looks like first order, from the other side it looks like second order, but nobody other than Nagel liked this term, so essentially it died, and he eventually gave up with this idea, and everybody now calls it the Castelline transition. Okay, so what would happen if we're not exactly in the limit where KT is much more than J? Well, essentially, we'll get something that would look very similar, but it will be rounded off by fluctuations, right? So if KT is not much smaller than J, some point-like excitations are allowed. And essentially what will happen is that you can now break these strings into bits. So the beginning and the end of one of these strings will have these monopoles attached to them. But now I will be able to have, even on the high field side, we'll be able to have some shorter length strings. So I will have some excitations on the other side. But still, we'll expect to find a very anisotropic type of susceptibility. So that will be the distinguishing feature of this susceptibility. Okay, so I don't want to enter into any of the experimental details. This is work, as I said, that we done mainly with Lucas and Chufo. What we wanted to do is to compare and contrast two different materials, so holmium and dysprosium. And the idea behind that was that we had these two materials that had essentially the same value for their magnetic moments. So we're expected to find this transition at the same field temperature ratio, but they had a very different exchange constant. So for dysprosium titanate is of the order of 1K, and for holmium titanate is of the order of 1.8K, so almost twice the value for dysprosium titanate. So the idea was that if you're looking for a transition that should not be dependent on J, it's good to have a system with very different J's and see what happens, right? Okay, so these are some experimental results. This is the magnetization for dysprosium titanate as a function of field compared. So these are the solid lines. They're compared with what you get from a paramagnet, and you can already see that the race towards saturation is sharper for dysprosium titanate than for a paramagnet. But when you look at the susceptibility, simply the derivative with respect to field of these curves, you find that while it's true that at low temperatures and high fields, the system does look like a paramagnet, I mean, follows, if you want, the scaling of a paramagnet, the behavior as a magnetic field is quite different, quite distinct. So here, instead of just monotonically decreasing susceptibility, you get this sort of asymmetric type of peak. So if you now look at holmium titanate, you see for holmium titanate, the exchange constant is higher. So that means that for the same temperatures, you're closer to the ideal limit. And you see that what you find is that this susceptibility is becoming sharper. So you get better defined, more asymmetric peaks. So now when you compare this susceptibility with the ideal susceptibility that you can calculate in the absence of any type of excitations, you see that they indeed resemble a sort of rounded off version of the ideal Castellani transition. So you can now construct a phase diagram using both dysprosium and holmium titanate. As I said, if you're looking for something that is independent of the exchange constant, you expect to find a universal line, and that's indeed what you find. So if you now compared this line, this is, as I said, green is dysprosium, red is holmium, and these are different measurements we've done with different techniques. You see that essentially you get some sort within experimental errors, let's say, get some sort of line. You compare that with the Castellani line, you calculate in the nearest neighbor model, and you see that it's similar, but it's not exactly the same. But when you do the proper calculation, so you take a Hamiltonian which includes dipolar interactions, and you see that here dipolar interactions are important because we're talking of systems which have magnetic moments of the order of 10 Bohr magnetons. So when you see that, you see that when you do the calculation with the proper Hamiltonian, see that essentially what you're getting is some sort of universal curve that's giving you this Castellani type transition. The one thing to say here is that okay. Okay, yes. So the question now is, if you have these lines, as I said, you have these shorter lines, is there any other way in which you can see these lines, or you can detect these lines? And this comes from earlier work we did with neutron experiments. And essentially, the idea is the following. So if you have a region where you have strings of negative magnetization, then you should be able to see those as observables in a neutron experiment. So yeah, sorry. One thing I wanted to say before was that the main difference between these two lines is that here in the nearest neighbor approximation, essentially there's absolutely no interaction between these lines you've created, while this is not necessarily true, and that's the difference. That's why this line shifts when you have dipolar interactions. So once you add the dipolar interactions, you see that these lines interact with each other. They don't particularly like being next to each other, right? So in a sense, I would say that these are not completely unlike vortices in a high TC superconductor, although they would be like the opposite of vortices, in the sense that this is decreasing the magnetization rather than increasing. Okay, so going back to the idea on whether one can get some sort of direct between vertical observation of these lines, you see that because you get these sort of random walks along the field direction, now you can calculate the correlation function for that, and this is what you get, and you can compare that with the experiment. And again, within the noise of the experiment, it's not too bad. But if you're not fully convinced, or we were not fully convinced, you can think about this now. Now you say, okay, I'll tilt a little bit the field. And what that would do is, instead of having these completely random walks along the field direction, I will have biased random walks, right? So if I look from the top, the random walks would tend to move towards one direction. So now when I calculate the correlation function for that, that would give me a correlation function which is elongated along one direction, right? Because there's a better defined correlation in one direction than the other. And if you compare that with the experiments where you tilt the field, you see that again, you get something that resembles the theory. Okay, so the last bit, I want to use the last 5 minutes of this talk to try to explore in a bit more depth some of the details of the material in this sense. So as I said, what we started with one description of the spin ice in very general terms, and we saw that there are many instances or many experimental observations of properties of these materials that match well with that. But of course, it's a model with an approximation, and as we saw along the different things we've been discussing, there were always caveats. So in some cases, I said, okay, well, so we didn't take into account the polar interactions. And one thing I didn't mention is, which maybe in a different format someone could have asked, is why didn't you do the experiment at lower temperatures? And that would be better, for example, for the Castellan transition would be better because you would be closer to the ideal limit. But the problem is that spin ice freezes at low temperatures. So if you go below 500 milli-K, the characteristic time becomes of the order of hundreds of seconds, and let's say at 100 milli-K, the characteristic time is of the order of a couple of months. So, and that's of course nothing you can explain with the Hamiltonian, not even with the addition of the polar interaction. So one thing we wanted to know was whether we could get from the experiment some kind of realistic effective Hamiltonian for this prosium titanate. So this is one ideal representation of the prosium titanate. This is a sort of pyrochlore lattice representation we always use. And the simplest realistic Hamiltonian one can think is one where you take into account nearest neighbors, next nearest neighbors, and third nearest neighbors. So you see that of the third type of nearest neighbors, you have two kinds. You have one kind which goes along this direction and the other kind that goes along that direction. Then the dipolar interactions and of course the interaction with the field. So the question was whether one could determine these from experiments. And one of the nice thing about current day neutron experiments is that you get a lot of data in a short time. So you can do an experiment for 4 or 5 days and you can get a terabyte of data out of that. So essentially the problem is no longer how to measure properties, but what to do with the data once you have it. So this is what I'm going to try to discuss in these last 5 minutes. So what we did then was to measure diffuse scattering for dysprosium titanate. This is the isotopic dysprosium titanate, and we chose a temperature. This is 680 milli-K, that it's low enough that we see correlations, but it's high enough that the system is not frozen. Right. So then what we did was essentially something where one would say it's quite simple. So we took that long Hamiltonian and we simulate and we try to fit the parameters so that the calculated neutron diffraction would match the experimental neutron diffraction. And okay, so we tried many different approaches, and so 1, 2, and 3 didn't really work, in the sense that there are so many different minima that we're talking of some sort of a 5-parameter fit. So you can narrow it down a little bit in the sense that the dipolar term is determined by the distance between dysprosium atoms and the magnetic moment. So and maybe you can use some other experiments to fix more or less J1, but at least it's a 3-parameter fit you need to do. So the one thing we did, which started working, but is what I'm calling this bio-inspired optimization. So essentially what you do is you take many different copies of your Hamiltonian and you put them in this parameter space and you start fitting in parallel to them. But not only do you try to fit them by minimizing the difference between, this is your cost function, right? The difference between the experiment and the simulation. But what you do is you let your Hamiltonian look at what other Hamiltonians are doing. So this is like if you want a flock of birds. So if you have one Hamiltonian that sees that lots of Hamiltonians are moving in one direction, this Hamiltonian would also like to move in one direction in parameter space. So the idea of that is that with that you can avoid being trapped in local minima. And as you see, so I'm plotting here some of these Hamiltonians. You see that the Hamiltonians start clustering along a particular region, and that's essentially where your optimal data is. But this is still too noisy. I mean, it's impossible to determine a set of parameters from this data. So we had to improve a little bit more. So we took a critical view of our data. This is the raw experimental data. And you see that there are different issues here. One is, of course, with any other experiment, there's noise. There's noise everywhere. But you also see that there's some missing data. So these are bits where either you have some shadow from a can or something in your experiment, and also you have the nuclear Bragg peaks, of which you're not interested, right? So we're interested on the magnetic part, not on the nuclear part. So the idea, and this was something that mainly Alan and Jana came with, is to use these autoencoders. So this is something people have been working a lot with, because it's essentially trying to analyze images. So this is the idea. The idea is that you take a neural network and you ask the neural network to give you back exactly the same thing you put in at the beginning. But the trick is that your neural network doesn't have enough bandwidth to carry all the information to the other side. So it has to lose a lot of information in between, and it has to learn what information it should lose and what information it should keep. So the example I have here is this sort of mushroom. You see, there's a mushroom that has shades and it has all sorts of nuances. But on the other side, you get something that you can still recognize as a mushroom, but you've lost. So the amount of information you have here is a lot less than information you have there. So the trick here is to make your network learn how to give you back, to take your data and give you back your data without the noise, without the missing parts, and without the Bragg peaks. So what we did was to take simulations and add noise and Bragg peaks and missing parts to the simulations, and then you ask the neural network to give you back the original simulation, right? So and you try this many times till the neural network learns how to give you back what you're looking for. So this is how it works. Then you take the raw experimental data, you put it through this autoencoder, and you get the output, which is the filtered data as well. This is the same as that, but you see that this missing bit is no longer there. These Bragg peaks are no longer there, and well, you cannot see it, but some of the noise is also gone too. Okay, so now you do the same thing than before. We will make this flock of Hamiltonians. We do the fit, and you see that you go now from what we had before, which was this light blue region. Now you got into this dark blue region where the Hamiltonians start to flock. So your optimal parameters are much better constrained now that you no longer have the noise coming from these unwanted features. So how good is this fit? Well, okay, so this is the raw experimental data, this is the latent data, and this is the fit to that data. You see that the fit is practically the differences between the fit and the latent data are extremely small. Okay, so now you know how to fit, but there's one particular thing which is a bonus that you get from this, which is now you can, if you want, open up the bonnet of this neural network and check what each neuron has learned to do. And what you see is that, so we had this system, I think it's 16 or 20 neurons, 24 neurons. And you see that each neuron, what it did was to learn how to recognize one particular feature of the data. So now you can, if you want to mix and match, you can ask, okay, of this particular feature, where would I find that feature on phase space? And that's what you get here, right? So this would allow you, if you want, to construct new materials, theoretically, of course, based on what you've learned from this fit. That's just a bonus. I mean, it's not what we were looking for. Okay, so going back to the experiment, now that we did this fit to neutron scattering, we said, well, maybe we can add more information. So like heat capacity or susceptibility. Now you can combine all these different sets of data and put them together, and you can narrow down the region where you get a fit to your parameters, right? This is J2, J3, and J3 prime. And this needle here is the region where the fit minimizes the difference to the experiments. Okay, so now you can say maybe that, okay, I don't like all this idea of these neural networks. I don't like, I think that what you're doing with that is you're getting fake data and you're fitting fake data. But the good thing about this is that once you have a fit, once you have a set of parameters, you can forget about the way in which you got that. So forget about the neural network, forget about all the filters. Then you take those parameters, you put them in your Hamiltonian, and you compare directly with the experiment, and you compare with the experiment under different conditions, right? So we did this fit at 0 field, and now, for example, we can compare what happens with the magnetization of the Rankine field between the data and the fit, And here you have neutron patterns for different fields. For example, this is for 0.2, 0.6. This is the original 0. And you see here that the left side is coming from the experiment, and the right side is the simulation, and you see that the fits are very good. So this is for 680 milli-K, this is for 900 milli-K, 0.2 Tesla. So essentially what this method allows you is to get a nice effective Hamiltonian to describe this material, but it also gives you more information. The first thing, as I said, is that you get information about how to create new materials, and the other is that it tells you not only where your system is, but what happens in the neighborhood of your system. So this is, for example, I'm showing you here the parameter space J3 prime, and this point here is where dysprosium titanate sits, right? So, but you can see that these colors here correspond to distinct patterns in your neutron experiment. So they correspond to distinct different types of long range or short range order that you get in this system. So small variations of these parameters make huge differences in where you sit. And this is not, if you can say that it's not altogether surprising, in the sense that, as we said from the very beginning, we're working on a frustrated system. So there are many forces that are being balanced. And as soon as you add external perturbations of some sort, for example, in this case, we're adding further neighbor interactions, even though they're small, they can make big changes in your system. Okay, so I think that maybe I went a little bit further than what it was expected for the talk in terms of time, so I should stop here. Just to conclude, I tried to present a case of one particular, one could say, simple frustrated system, this spin-ice type of systems. And I tried to explain to you why we like working on that, why we're interested in it. And I gave you a couple of examples of some of the interesting things one finds in terms of its physics. And in the end, I also tried to tell you a bit of some of the methods we've been developing to study this sort of systems, which I understand can also work for more generally for other type of systems. So, okay, thanks for your attention.
Okay, so if you want to remove your mute and thank the speaker.
Bravo. Bravo.
Okay, so I don't know if there are any questions over there, so please help me, or just unmute your phone and ask right away. I don't know if I would be able to see your raised hand, so you tell me.
Okay, I have a question, Chufo. If I
okay, yeah, go on.
Okay. First of all, thank you, Santiago. Very nice talk. Really clear. Okay, my question is related with the first part of the talk, and when you have a Castellane transition, and you showed a neutron scattering experiment when you have a very nice peaks related with the contribution to this string excitation. I think it's in maybe 30, slide number 30. No, previously.
Yes.
Yes, the two.
This one.
Yes, this one. Yeah, good. My question is related with the effect of the temperature. This is is there a window in temperature when we can find this contribution to the string excitation? And the other question is if in a network scattering you can find any evidence of the local excitation. I mean the charge. Maybe related or connected with the pinch point that you talked before.
Yeah, yes. Those are yes. So let me start with the problem here again is what I said about the freezing of spin ice. So essentially, the window we have for looking this is very narrow. So you need to be below 1K, because of 1K, your J is of the order of 1K. So at 1K, you're getting too many excitations to try to get these sort of lines. But at 600 millik, the system starts freezing. So you need to be this one that I'm showing here, the experiment, which is not seen here. So that experiment is at 700 millik.
Okay.
So it's a really narrow region where you can see it. And essentially, part of the evidence for the point-like excitations come from the fact that you can match the experimental part closer to a system with short, well, not short, let's say with non-infinite or finite strings rather than with infinite strings, right? So the only way in which you get these finite strings is if you cut the ends, and if you cut the ends, you need to put charges at
yes, okay.
So that will be the simplest way of saying, yeah.
Okay, thank you.
So I don't know if there are any questions in YouTube. Maybe someone is. Okay.
We have one question. We have a question from Kleber Roberto Pirota from Unicamp. He asks, to observe such a rich phase diagram, especially spin fragmentation, is the crystalline structure to be a single crystal important?
Especially, well, in principle, it's not, right? So, for example, it depends what you're looking at. But for example, if you were looking at something like these measurements I showed you of the specific hits at the beginning that we were matching with the bihucal, well, there's no problem there. You can use, you can certainly use a polycrystalline sample, and you will get exactly the same results. So, of course, once you start exploring other type of things like this Castellan transition, where you need to define directions in space, and you need to match those with crystalline direction, of course, you need to have single crystals. But a lot of the physics is independent of whether it's a single crystal or a polycrystalline sample. For example, I think, I'm not completely sure, but I would bet that these, I'm not sure if I'm still sharing this screen. I think I am. Yep. So the work by Ramirez here, this measurement where they determined the residual entropy, was done on polycrystalline samples. And yeah, so essentially the answer is, it's nice to have single crystals, but it's not necessary. And maybe the other thing I should say, it's something which is unusual for this type of materials, which is it's not too difficult to grow single crystals of these materials. So in some other cases, it's a real nightmare to get a good quality single crystal. For example, some of our previous work was on strontium titanate, and there was a real nightmare to get a good single crystal. Here, the first time we decided to start working on something like spin ice, I put that as a summer student project to grow the crystals, and maybe she was a very talented summer student, but an undergraduate managed to grow these crystals within a couple of months.
Okay.
Thank you.
So maybe you said it while I was chasing after questions, but also if you are putting an applied field, if you are applying a field, it would also make sense if you have a single crystal, doesn't it, Santiago?
Yes. I thought I said that. So one.
Okay, sure.
Well, for example, for the Castellan, where you need to identify a direction in space that corresponds to the direction in the crystal, then you need to
So if I may give some time for more questions, if I make a question myself. So in the swarm method for
Yes.
finding your true Hamiltonian, so there what you do, if I understood correctly, is you propose different initial conditions and also some sort of randomness to you treat your, is that right, to your different Hamiltonians. So you propose different initial Hamiltonians, let's say, and you let them move according to some sort of Monte Carlo or least squares method combined with least square method, and you add some randomness to it. Is that right?
Yes, you can. So you can do it with randomness or without randomness, but yes. So in our case, we did it with a little bit of randomness. So essentially, the fact that you take phase space and you do some sort of a homogeneous distribution of these Hamiltonians, that's already saying that you're setting different parameters for each Hamiltonian, and then you let them evolve in the path where they start minimizing the difference with the cost function. But you add two things. One is, as you said, you can add a bit of randomness that looks a bit like some sort of you can do it in a way of an annealing, right? This sort of simulated annealing. And in addition to that, is that this term, which is essentially looking at this is very similar to what people do in flock simulation of birds. So you take some sort of a radius, and there you look at what's the average velocity of the rest of the average velocity of the Hamiltonians, and you add to your Hamiltonian a term proportional to that. I don't know if what I'm saying.
Yeah. Okay.
Is clear.
Okay.
But so essentially, what that means is that even though your Hamiltonian might be wanting to get stuck on one local minimum, if there are many others moving in another direction, it would eventually go away from that, even though it would temporarily maximize, so it would temporarily increase the cost function.
I see. Okay, thanks a lot. So I don't know if there are any other, let me check there in chat to see if there are any other questions. So I do not see anyone there. I don't know if anyone raising his or her hand. I do not see it.
So, okay, maybe I have a last question, maybe very short.
Go on.
But
yeah.
Okay, because again related with the Castellan transition.
Sure.
And maybe it's related with the previous question. It is important the three-dimensional of the material to find a Castellan transition, because you mentioned it, for example, another lattices like Kagome or I don't know, but frustrated lattice. And it's possible to find a Castellan transition in this material.
Yes, you mean
okay.
Yes.
Okay, but it's not crucial to have a three-dimensional material.
No. This is a nice example of a three-dimensional Castellan, but as a matter of fact, the original Castellan, it's two-dimensional. It's
okay.
dimers in a two-dimensional lattice. And there's one other Castellan transition that we haven't looked for in spin ice, where you put a field along 1, 1, 1. So you polarize, if you look at the pyrochlore along 1, 1, 1, it's like stacking Kagome lattices and triangular lattices.
Yeah.
And what you do with the field is you first freeze the triangular lattice, because those are full in the direction of the field, and the other are not. So you reach the regime where you have what people call Kagome ice, which is some sort of an ice in the Kagome planes. And then if you tilt the field, people say that there's also a Castellan transition.
Okay. On the plane, on the Kagome plane.
Yes.
Okay.
But we
Good.
haven't looked for that.
Okay. Good. Thank you.
So I see there is a question from.
I have a question.
Okay. I don't know who was first. I saw this one by Kike. So as you want, you go on, Flavia. Kike, I have taken note of yours. Let's go first, Flavia, and then Kike.
Okay, sorry, Kike. I'm sorry. Okay, thank you, Chufo. Thank you, Santiago, for the great talk. I would like to ask you regarding the family of Hamiltonians that you get from machine learning at the end.
Yes.
So, I mean, there is a great agreement between the data and the Hamiltonian that you have optimized. I understand this is a very broad question. So have you explored what differences the other Hamiltonians, I mean, if you have, I mean, for example, you know the orange area you're showing there,
Yes.
right? Does it have basically the same phenomenology, or is the difference significant, would you say?
Not within the, so the colors are chosen so that it's essentially, how would I put it? So the short answer to the question is that the colors represent different regions. So within the same color, you expect similar behavior. This is only based on the neutron data, not on anything else.
Oh, okay. Okay. So the other thing would be a great deal of work, right? To see exactly what difference you expect in all the region or something like that. Okay.
Yes, I mean, as I say, so we know essentially what we can do now is we can simulate. We do Monte Carlo with the different Hamiltonians and we check what happens. But the other thing we're doing, that's essentially work in progress, and this is one of the nice things about the pandemic, is that now we're allowed to mail the samples to the lab. We don't need to go. So we're doing, right these days, we're doing an experiment on Oak Ridge, but I'm here in La Plata. That's very nice because you don't need to be there. I mean, there are technicians who do the work and you get the data. Essentially what we're doing is we're putting uniaxial pressure, and not only uniaxial, but also hydrostatic pressure, to see whether we can make small changes on the J's so that we can move the material towards some of the other colored regions. That's the idea. The first bit we did, which was hydrostatic, I mean, you never know how it's going to move. So the first thing we did was hydrostatic on the dispersion titanate, and we went deeper into the orange region. So we got essentially nothing. So it's more of the same.
Okay, so you would look at the neutron scattering and see whether it is one of these regions or something else happens, right?
Yes, but for the time being, as I said, we went deeper into.
Okay. Okay, thank you. Thank you, great.
Okay, so Kike, if you want to unmute your phone.
Yes, well, before of all, thank you very much for the talk. It was very interesting, the materials, the physics and the methodology that you employed. But this is, I was wondering, it's a very broad question. In which other fields of physics or science or even beyond science, frustration is important? If you can comment anything about this, and whether some of the approaches that you have used for analysis and exploration can be translated to other fields.
Yes. Okay. Thanks. Yes, it's a very broad question. What I would say, let me start first from the narrower, and then I go to broader. From the narrower, I would say that some of the methods are very easy to export. For example, this last bit we've been doing on filtering of experimental data. I think that in principle it can be used to any system you want. So the idea that you can identify some sort of systematic systematic sources of noise for measurements and standardize this. I think that's something that can be exported. I would say that there's nothing specific about what we were doing on that. And again, this idea that we as physicists can tap on a lot of work that has been done by computer scientists. So essentially, because nowadays people are so interested in images and treating images and essentially Google is working all the time on trying to find images. That means that they need to develop methods to look for the relevant bits of an image. And I would say that looking for relevant bits of an image is not that different from looking at the relevant bits of data you get from one experiment. I would say that that's one part of this work that can be generalized. And in terms of frustration, I would say that that it's not unlike the rest of the talk. It's not particularly special, I would say. So it is like the rest of the physics. I would say that in each of the things, all of us are working with fine bits that are easy to, that would be relevant to other work, but I wouldn't single out frustration as something special. I mean, it's something we like, it's something we enjoy, but I wouldn't be so. I mean, so full of myself as to say that frustration is particularly special. I think it's nice, and maybe we can say, because most of us, I guess, we're physicists, or at least like physics, we can say that physics is special.
Okay, well, thank you very much.
Thanks, Kiki, for the question. So I cannot see any more raised hands. So I don't know if it's time then to thank the speaker again.
Sorry, Truffaut, there is one in the chat I wrote from YouTube.
Ah, okay, thank you.
Do you want me to read it?
I'll go for it. So
Okay.
A question in YouTube from Edwin Ramos. Thank you for the nice talk. It is evident that the interesting physics in those systems. What so hard is to create artificial frustrate systems to transport chiral spin currents is the question.
Okay, so I would say that the problem with creating artificially frustrated systems is that it's very easy for things to go wrong, in the sense that you need to balance. The problem with frustration is that forces need to be balanced. So there are some examples of artificial spin ices, but they're very, very limited in the sense that it's not easy. So what I'm trying to say is that the system would immediately find ways of getting out of frustration. So as soon as you get some sort of possibility of distortion, the system would distort an order, or if in your system you get anisotropies, the frustration would be killed. So in principle, theoretically, I would say it's not impossible, but it needs a lot of effort. That would be the thing to say. It's not impossible, but it's not easy at all. And there are a lot of people interested in pursuing that avenue, the construction, if you want, of artificial frustrated systems. And there are ways in which you can create frustration in artificial systems that are interesting by themselves, that you cannot get in crystals. For example, there are people who are thinking about Möbius strips for frustration, in the sense that if you can add, if you can connect surfaces in special ways, you can also frustrate spins in particular ways. And I would say that it's a very interesting avenue of research, but also not a simple one.
So one part, maybe you, okay, maybe you already answered it, Santiago, but you judge it. He says, he also asks, so Flavia probably writing this, he asks if these systems are robust.
Spin ice. So dispersion titanate and Holbein titanate are very robust. That's one of the nice things about them, that they're very hard, so they do not distort. As a matter of fact, what we're finding is that once you're happy with the things you've done with the undistorted system, it's not so easy to distort them. And and they're very chemically stable. So in that sense, they're ideal systems to work with. And maybe that means that they're very good systems for applications. But yeah, if you want, there's always this double-edged sword. So that the system is robust also means that you cannot fiddle with it a lot. So when you want to make changes, when you want to start tuning the system into different aspects, you find that robustness, which was a friend at the beginning, becomes a bit of a foe.
Okay. I thank you then, Santiago. I don't know if there is any feedback from there, Flavia.
No, everyone thanks Santiago.
Okay then. Okay then. Let's thank again the speaker. If you want.
Hey, thank you very much for
your invitation.
Thank you, Santiago.
Thank you,
Thank
Santiago.
you. Excellent talk.
Thanks.
Thank you, Santiago. Bye-bye.
Okay, perfect then.
Great.
So Paula, then the control is yours. So I don't know if you have any other comments or things to say about next talk or whatever. So I'll unmute now my.
Next talk will be in May. I think it's the 21st by Gabriela Paschini. And please stay tuned and you will hear from us by